right, so 4.2. Okay, so we're looking at natural exponential functions. Okay, so the natural exponential function, so this is specifically where the base is e. All right, so first, like why are we calling this the natural function? And where does this number e, which is approximately 2.72, where does it come from? All right, well, first off, e is very similar to pi, right? As we've talked about before, pi is 3.14 or approximately 3.14. Okay, that's the ratio of the circumference to the the circumference to the diameter of the circle, whereas the base e, where does this come from? Where does it occur naturally in the world? Okay, so we're going to look at this formula that we know. So this is A of t is the principal times 1 plus the rate over the compounding times the compounding and the time unit. All right, so what we're going to look at, though, is something like sort of a variation of this. So we're going to look at when the principal is 1. Okay, so when we're starting with one item. So we're going to look at where p is 1. All right, so just 1 plus. And then we're going to look at something where the rate, it doubles. So it's 100%. You might be like, 100%? What bank account gives 100% interest? Well, 100% is actually something that does happen in the real world. So we're thinking about maybe populations, right? So rabbits, they can double. All right, and they do literally double, or more than that, actually. And it doesn't take them a year to double in. So we're going to look at a rate which is 100. But in terms of plugging it into our equation, it's actually going to be 1, because that's 100 over 1. 100 over 100, which will be 1. All right, and then n. And then we're going to be looking at, in terms of 1, okay, times n. All right, so let's take a look at this in terms of, let's say our item, whatever we're talking about, maybe our population or something, let's say we compound it at half a year. So half a year. So n would be 2. So looking at that, we get 1 plus 1 over 2 times 2. Plugging that into your calculator, what do you get? That's going to be 1 plus 0.5 to the second power, which is 2.25. All right. Interesting. Not really, not yet. Okay, so that was half a year. How about, let's look at something that doubles monthly. What value would we get to? So monthly is going to be 12. Plugging that in. Oh, interesting, 2.61. So we went from twice a year to monthly, and it only went up a few decimal values there. Okay, let's talk about maybe daily. Daily, we're going to use 365. Plug that into your calculator and see what you get. 1 plus, oops, that's a plus sign. 1 divided by 365 to the 365. Oh, that's so weird. Look, we went from 12 to 365, and we still only went up like a few decimals. That's so strange. How about, instead of daily, let's look at a million. Why not? Let's see if we can make this value come out bigger. Okay, plug that into your calculator and see what your number is. Voila! It hasn't gotten much bigger at all. We went from using 365 to a million, and we just went up a teensy-weensy amount. Okay, so this is something mathematicians noticed when they asked the question about something doubling, starting at an initial value of 1, so a population, and we found out that the number, the larger and larger, so the more and more you compound it, In fact, they were trying to figure out something that just compounds continuously. Okay, like population, we really don't know when someone's going to be born or something, or some fish are going to be born. So it's just compounding continuously. And when we get that, as the numbers get larger and larger, compounding, the value still just approaches this number. And so the person who decided to coin it as E, I think, was Euler. He was a very brilliant mathematician. You should read into him sometime. A very interesting person. So he decided to coin it as E. I believe he was the person who chose that. So E is approximately the number 2.72. And it comes kind of from this concept here. Or it comes from this concept. All right, so we're going to just go ahead and sketch what e to the x looks like. So I'm going to give you some values to go ahead and sketch with. Okay, so plug them into your calculator and check in with me. All right, so I'm going to do the first one with you in case finding E. So let's just remember how to find E. So finding E on your calculator, E is where the natural log button is. I don't know if you can see. Oops, it's not going to focus. Focus. All right, right there, e to the x. So to find that, it's in blue, notice. So remember, you're going to hit the blue button and natural log x. And there's your e. And we want to the -2, which is about that value there. So I'm just going to round to 2 values, as per usual. Okay, go ahead and fill in those other values. Check in with me in a second. All right, filling those in, let's see. Okay, so I went ahead and did those in my calculator. All right, so let's go ahead and graph these items. I'm pulling out my thin graphing pen here so I can fit all my values in. So we're going to go with -2, 0.14. -1, 3.6. Zero, 1. 1, 2.72, about there. And 2, ooh, that goes off the chart. About there. 2, 7.39. Actually, it's probably a little lower than that. All right, and let's draw this in. Question, do we have a horizontal asymptote? Answer, yes. Because, ask yourself, can I ever raise e to some power to get 0? No, it's not possible to raise a number to a power and get 0. So we have that horizontal asymptote, y equals 0. Ooh, and that's out of focus. All right, there we go. Sorry, that was out of focus for a bit. All right. Okay, so moving on to I think this is the last page for this one. Yep. All right, applications. So we're looking at, remember, this was how we found E, something that just continually compounds. Okay, so we're looking at continually compounded interest, very similar to the one that we had before. So we have our principal. Here, though, we have E instead, times the rate times the time. Okay, where T is in terms of years. Okay, good to note. All right, so we have a certain drug is administered to a patient, and the number of milligrams remaining in the bloodstream after T hours is D of T. Okay, so we're given this. I'm going to change out to a better pen here. D of T equals 50 e to the 0.2 t. I like these pens for writing. This one's way better for graphing because that's such a thin, fine point, but it makes my writing look horrible. All right. So how much of the drug remains in the patient's bloodstream after 2 hours? Okay, so here we go. We're given 2 hours, and we want to know D of T at 2 hours, or after 2 hours. Okay, so we're going to plug in 2 for T and solve. All right, so that's going to be D of 2 times 50 e to the -0.2 t. And I want after 2 hours. All right, so plugging that in to our calculator. Real quick, let me just simplify this out on the top. All right, we can plug that into our calculator now. And we'll get 50 times e to the -0.4, which is 33.51. Okay, rounding 2 decimal places. Oh, Actually, they tell me to round 2 decimal places. So that's going to be 33.52. So D of 2 is approximately 33.52. So what's my answer? So how much of the drug? About 33.52 milligrams. We're talking about milligrams here. Of the drug remains in the patient after 2 hours. Okay, nice. Not overly detailed answer, but it lets me know exactly what we're looking at. All right. Okay, so next, let's look at the population. This is the last example. The population of a certain species of bird after T years is given by this very large function. So first we want to find the initial bird population. Well, what does the initial population mean? That means the starting population. Starting at, well, normally you start at time 0. Okay, so we're going to start at t equals 0. So we're going to start at t equals 0 and find n of 0. Okay, so what does n of 0 equal? Well, plugging that in. Oops, sorry, that's 27. Oh, and my whiteout is dead. What a time is this to have your whiteout die on you. All right. When you can't even count on your whiteout. All right. We want t to be 0. So we're plugging in 0 for t. Right there. Okay, plugging that in. Well, anything times 0 is going to be 0. So we'll end up with e to the 0 power. Which means we're going to get 5,600 all over 0.5 plus, well, e to the 0 power is just going to be 1. So we'll just be left with 27.5. All right, and then we'll get over 28, which simplified is 200. So my answer, the initial bird population was 200 birds. All right, part B. As time goes on, what size does the population approach? Oh, we're asked to look at the graph. Okay, so we're going to go ahead and graph this, but first I want to figure out what window I'm going to look at here. Okay, so let's see. Thinking about when we're graphing, remember with x and y. Actually, wait, can I fix this? Because I want to graph what we find later. Why is this continually just dying on me? Not the most trustworthy of whiteouts today. His brother just died. I used him up already. Okay. So let's see. X values. So the x's, generically, it's x, but we're looking at t. So these are t values. T values are years. And my n of t values, which are actually my y values, that is the bird population. Okay, so in terms of years you normally don't count negative years. So we would have our window of 0 to, maybe let's do 150 years. That's, 150 years. It's not outrageous. All right, and then let's see, bird population. Normally you don't start at a negative, so we'll start with 0. And then bird populations can get pretty big. So let's maybe do 20,000. Okay, and then for our scales, so like how, if we're going in terms of 1s or 2s, maybe for the years, let's go with scales of 10. And then for bird population, maybe 0 to 2,000. 10 would still be kind of a small scale. So let's go with scale of 100. Okay, let's go ahead and plug these in. Okay, so first we're going to go ahead and plot in our values for our graph. So I already went ahead and did that. I have the 5,600 divided by, and my value here. Okay, but notice one thing about our calculator. We do not have, or we cannot use the variable t for graphing. So you're just going to go ahead and use the generic x value when you're graphing. Okay, so when we hit graph, actually we're going to go to window first before we hit graph. And let's see. Okay, so my window is really weird. So what I'm going to do is change my window. My minimum value I said was 0. My maximum value I said was 150. Let's do that. And I scaled it by 10. Okay, that's good. It's still scaled at 10. My minimum y value I'm going to set to 0. And then my maximum y value I'm going to set to 20,000. And then my y scale, oh, it's already at 100. I'll keep it at 100. Okay, so there we go. We went and scaled that. And remember, that was our window calculation button. So now we're going to hit graph and see what our value approaches. Oh, there she comes. There she comes. Look at it. Oh, okay, so kind of starts to level out here, but I don't know what that value is. So maybe I made my x values too small. So I'm going to extend it. Maybe I'll extend it to, let's go with 250. We're going to extend it to 250. So 0 to 250 years. Let's change our window real quick. So I'm going to make the maximum x values. This time I'll extend it a little further to the right, 250. And let's try graph this again. Let's see, can I see where it flattens out? Ah, look at that. So my graph, the population rises, and the population starts to naturally level out. Okay, kind of like in nature. So I want to figure out what that value is that it's leveling out at. So let's hit trace. Okay, there's my button. I want to see where it starts to level out, so I'll just continually go to the right. See, my y values are changing and the years are changing. So at the year 194, my bird population was 11,081. So let's keep going. Here's where it really levels out. So at the year 250, my bird population is 11,189. So that's kind of the value it's approaching. So the value approaches, that's getting close to, oh, sorry, pull this over. It looks like it's getting close to about 11,200. So the size of the population approaches 11,189. Actually, you know what? I said I was going to round this up. So it depends on how they want you to show your answer. But we're just going to round up to 11,200 birds. Okay, so that's what it approaches that value. Okay, so if you wanted to, we could widen our window a little further just to check that. So instead of 250, we could go to 300 for the years and try graph that and see what we get. Okay, and then when we trace it, yeah, see, look at that. No matter how far I go, the value is still, it's only hit 198. So in fact, I could possibly, if we just keep going right and tracing it, it looks like it's not even actually hitting, see my y value there? It's not even hitting 11,200 yet, and I've been going for many, many, many years. Look at that. 434 years, and it still hasn't even hit 11,200. You could still go farther right, many, many more years. Oh, there we go. Look at that. More right, it stopped. I stopped us too soon. Look at that. 510 years, and it's finally hit 11,200. I'm going to go way more years. Let's see. Look at that. I've gone to 561 years, and our y value has stayed at 11,200. Okay, so that is the value that our population is approaching, right? 11,200 birds. All right, so that is it for 4.2. Here's the written homework. Please email me if you have any questions.